In the first part of Precalculus Lesson 19, we begin by finding the domain of logarithmic functions and then move on to developing a strategy for solving logarithmic equations. This lesson is from section 4.4 in the college algebra textbook. Let's start by finding the domain of f of x equals the natural log of 3x minus 15. If you remember when we graphed y equals the natural log of x, we could tell from the graph that our domain is all values of x greater than 0. So that's the case for any basic logarithmic function. Its domain is going to require the argument to be greater than 0. In this case, 3x minus 15 must be greater than 0. And so 3x would be greater than 15. Dividing through by 3, I find that x must be greater than 5. So my domain here is all real values of x greater than 5. Now moving on to g of x equals log of x minus 5 over x squared plus 4x plus 4. I begin by realizing I must have x minus 5 over x squared plus 4x plus 4 greater than 0, but I'm going to, at the same time as I write my inequality, factor the denominator into x plus 2 squared. So we have x plus 5 over x plus 2 squared is greater than 0. Resorting back to what we learned about solving rational inequalities, which is what we have here, I'm going to name this function on the left of my greater than sign f of x, since we already have a g of x here. And then if you remember, we set each factor in the numerator and denominator of f of x equal to 0. So we have x minus 5 equals 0, x plus 2 equals 0. And we solve to get x equals 5 and x equals negative 2. As endpoints of our solution region, we put those endpoints on a number line. We have negative 2 and 5, and then we test a point in each region here. So we could test to the left of x equals negative 2, I might test negative 3. Between negative 2 and 5, I would test x equals 0, and to the right of x equals 5, let's try x equals 7. Additionally, we need to make a note that negative 2 is undefined for this function. Since it occurs in the denominator, 5 would be a 0 of our function f of x. And now let's go on to test x equals negative 3. We'd have negative 3 minus 5, which is negative, over negative 3 plus 2 squared, which is positive, resulting in negative y values to the left of x equals negative 2. Plugging in 0, we have a negative over a positive for negative y values in that region. Plugging in 7, we would have positive over positive, which gives us positive y values to the right of x equals 5. So now what are we looking for? We're looking for strictly greater than 0, which would only occur to the right of x equals 5. So our domain for g of x is all real values of x greater than 5, or 5 to infinity in interval notation. Let's look next at solving logarithmic equations. A general strategy would be to rewrite the original equation in the form log to the base b of u equals y, or log to the base b of u equals log to the base b of v, if possible. If not, this strategy would not work. But let's go on to the case where we can rewrite the original equation in the form log to the base b of u equals y. And in that case, you can see that we could convert the equation to its exponential form of u equals b to the y. For the case where log to the base b of u equals log to the base b of v, we can use the one-to-one property of logarithms to rewrite the equation, or to reduce it to u equals v here. Once we've completed step 2 or step 3, we would solve the new equation to find potential solutions. But what we need to do here is we need to check each potential solution before declaring it an actual solution here. Let's go on and try some problems. First of all, we'll solve the equation log to the base 3 of x plus 3 minus log to the base 3 of x minus 5 equals 2. And first of all, I'm going to use the difference property of logarithms to rewrite the left side as log to the base 3 of x plus 3 over x minus 5. And now we have our equation in the form log to the base b of u equals y, so I can change forms into exponential form here, which would be 3 squared equals x plus 3 over x minus 5. So we have 9 equals x plus 3 over x minus 5. I'll multiply both sides of the equation by the denominator of x minus 5 to get 9 times x minus 5 equals x plus 3. Then distributing that 9 through, 9x minus 45 equals x plus 3. After which, we have on the left side, subtracting x from each side, we would have 8x on the left, and adding 45 to each side, we would have 48 on the right. If 8x equals 48, that would give me x equals 6. We can't quite call this a solution yet. We need to check it in each argument. So what I do is for our argument x plus 3, plugging in x would give me 6 plus 3. I don't really care what number it is, but I want to make sure it's positive, which it is. I plug in 6 for x in x minus 5, and 6 minus 5 is positive again, so we're good. And x equals 6 is indeed a solution here. Now moving on to solving log to the base 3 of x plus 3 plus log to the base 3 of x minus 5 equals 2. I think the only difference from the last equation is that we're going to use the sum property here on the left side to get log to the base 3 of x plus 3 times x minus 5. And on the right side, we still have 2. Well, we have already gotten this equation into the form log to the base b of u equals y, and so we'll change forms into 3 squared equals x plus 3 times x minus 5. The left side gives us 9. The right side we expand to get x squared minus 2x minus 15. And then subtract 9 from each side to get a 0 on the left. On the right, we then have x squared minus 2x minus 24, and we factor the right side, giving us factors of x minus 6 and x minus 4, or x plus 4. Okay, setting each factor equal to 0, we get potential solutions of x equals 6 and x equals negative 4. Okay, so let's test x equals 6. Looking at our first argument here in the original equation, plugging in 6, 6 plus 3 is positive. We check the other argument, 6 minus 5 is positive. So x equals 6 is a solution here. Let's go ahead then and check x equals negative 4. So to check x equals negative 4, I'll plug negative 4 in for x in the argument x plus 3. Negative 4 plus 3 is negative. So we can stop right there and understand that x equals negative 4 could not be a solution here. If we did check the second argument, we'd have negative 4 minus 5. That again would be negative. But as long as we found one argument that doesn't work, we can exclude x equals negative 4 as a solution. So our only solution here is x equals 6. Now let's solve the logarithmic equation. 2 log x minus log 2 equals log of x plus 4. This is log to the base 10. The first thing I will do is turn this 2 log x into log of x squared using the property of exponents. And so we have log of x squared minus log 2 on the left side. I can combine logs on the left side using the difference property of logarithms. So I would have log of x squared over 2 equals log of x plus 4. At this point, we have our equation in the form log to the base b of u equals log to the base b of v, where our base here is 10. So I can set x squared over 2 equal to x plus 4. The next thing I would do is multiply through by 2 to get x squared equals 2x plus 8. And then on the left side, let's subtract 2x and let's subtract 8 from each side to give us x squared minus 2x minus 8 on the left side equals 0 on the right. This equation factors into x minus 4 times x plus 2 equals 0. We set each factor equal to 0. Setting x minus 4 equal to 0 results in x equals 4. Setting x plus 2 equal to 0 results in x equals negative 2. We check each solution. The first argument here is x. Plugging in 4 for x would give us a positive argument, so we're good. Plugging in 4 for the x in x plus 4 would give us plus positive 8 here. And so x equals 4 is a solution. So let's try x equals negative 2. And first of all, we'll plug negative 2 in for x in our first argument. So that right there would give us a negative. So we cannot include x equals negative 2 as a solution here. However, note, if I would have started with the argument x plus 4, negative 2 plus 4 would actually be positive. So just keep in mind you do absolutely have to check every argument to determine if a potential solution is actually a solution. Okay, let's go on then to, after determining for this problem, x equals 4 is the single solution. Let's try solving the equation. 1/2 log to the base 2 of x plus log to the base 4 of x minus 1 equals log to the base 4 of 4x. The problem I see right off here is we have log to the base 2 in one of our logs, and the other two logs have log to the base 4. So I'm going to change this log to the base 2 of x into log to the base 4 using the change of base formula. Log to the base 2 of x would be equal to log to the base 4 of our argument x over log to the base 4 of our base 2. We can simplify a little bit further with this. We have log to the base 4. Can't do much with that, but log to the base 4 of 2 is the power of 4 that would give me 2. And if I take the square root of 4, or if I raise 4 to the 1/2 power, that would give me 2. And so I have log to the base 4 of x divided by 1/2, which is the same as log to the base 4 of x times 2 over 1, or 2 times log to the base 4 of x. So going back to our equation, we're going to rewrite our equation as 1/2 times, I'm replacing log to the base 2 of x with 2 log to the base 4 of x. And then we have plus log to the base 4 of x minus 1 equals log to the base 4 of 4x. Okay, so 1/2 times 2 log to the base 4 of x is simply log to the base 4 of x. Then we have plus log to the base 4 of x minus 1 equals log to the base 4 of 4x. I go on to using the sum property on the left side, from which we get log to the base 4 of x times x minus 1. And at this point, we have our equation in the form log to the base b of u equals log to the base b of v. So we can set x times x minus 1 equal to 4x. And from here we have x squared minus x equals 4x. I'll go on to solve by let's see, we need to subtract 4x from each side. I want to get a 0 on the right, so that would give me x squared minus 5x equals 0. On the left side, I can factor out an x from both terms, resulting in x times x minus 5. And then setting each of these factors equal to 0, our potential solutions would be x equals 0 or x equals 5. Let's test each of these, starting with x equals 0. Well, our first argument here is x. Note that I also, in addition to not being able to have negative values for my argument, I also cannot have 0 for an argument. Our argument has to be have values strictly greater than 0. So x equals 0 does not work. In fact, you can see if you plug that into our second argument here of x minus 1, it would definitely be negative there. Okay, let's try 5. So plugging 5 in for x is positive. Our second argument, we would have 5 minus 1, which is positive. Our third argument, we would have 4 times 5, which is positive. So our only solution here is going to be x equals 5. Okay, so moving on to try on your own number 1. Solve the equation log of 3x plus 1 minus log of x minus 2 equals 1.